This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, and this is Lecture 56, where we're going to talk about lithographic quality. So what is lithographic quality? There's four main classes, ways of categorizing the broad topic of how to judge the quality of a lithographic result. First and probably foremost, maybe not foremost, but one of the top couple of things you think about in lithographic quality is getting a good resist profile. That is, getting the right line width, the right shape of the profile, the sidewall angle, the angle that the sides of the profile make with the substrate. Line edge roughness, we're going to talk about that later, but line edge roughness is the smoothness of the sidewalls and as a result the smoothness of the line width. But we make more than just lines, we make patterns that have corners and have lots of interesting shapes, so the corner rounding and overall pattern fidelity. Important topics like resolution, depth of focus, or process latitude in general are essentially under the topic of profile control. What is resolution? The smallest pattern that allows us to keep adequate profile control. Depth of focus, the range of focus over which we keep adequate profile control, etc. So this is one of the main things we think about. The second main thing we think about is overlay. Not only do we have to print the right patterns, we have to print them in the right place. Overlay is the measure of the error between where the pattern landed on the wafer compared to where we wanted it to land, relative to the patterns underneath. Here we worry about the variations in overlay within a lot, across a wafer, and across one exposure field. A cross-chip pattern placement error is also important. This is more of how aberrations and other non-ideal imaging might cause some features to move a little bit to the left and other features to move a little bit to the right. While lithographers spend most of the time thinking about these two things when they think as a lithographer, in reality, of course, we're doing manufacturing. So we have some manufacturing-oriented things to think about as well. In particular, how does our patterns serve the needs of subsequent process steps? After all, we don't ship photoresist patterns to customers. Instead, those patterns are used for etch and for implant to transfer the patterns into the substrate. So we worry about etch resistance, thermal stability, adhesion, chemical compatibility, strippability. Ultimately, we have to strip the resist off when we're done, and things like pattern collapse. But then there's the whole class of pure manufacturability. Things like defect, cost, which is a strong function of throughput of our exposure tools, safety, environmental impact, and for all manufacturing processes, predictability or stability of the process over time. So of all these lithographic quality factors, what I'd like to talk about today is Linewidth Control. That's what the subject of the last lecture was as well, but I'm going to talk about one specific Linewidth Control factor, which is exposure latitude. To do that, I'd like to first think about lithography as a sequence of information transfer steps. Now this may seem a little strange until you go all the way back to the beginning. When we start to think about patterning, the first thing that we have is a design. A design is nothing more than a computer file. It has ones and zeros saying, well, this is where I have a rectangle, and inside the rectangle this is where I want metal to be, and outside the rectangle that's where I want metal to be gone, for example. The design data is pure information about the patterns that we want to print. The design includes metadata about aspects of the patterns that we're trying to print, besides the raw polygons that represent the shapes. But nonetheless, the design data is everything that we have in terms of the goals, the targets, the information about the design we want. Then we start transferring that information along the way. The first thing we do is fabricate the mask. The photomask is going to be our master pattern to image onto our wafer, And we use, in fact, a lithography process to create that photomask. But that process is not perfect. We don't get a perfect replication of the design in our photomask. We have some errors in placement, in line width, and we have errors in corner rounding and pattern fidelity. All of these things mean the mask contains less information or imperfect information compared to the design. We've lost information in that sequence. Then the mask is used to form an image. First an aerial image and then an image that propagates into the photoresist. But let's just think about the aerial image first. The aerial image is an imperfect representation of the information that's on the mask. It's imperfect because our lens is a low-pass filter. As we've seen, we have a cutoff spatial frequency of the numerical aperture divided by the wavelength, and all spatial frequency information higher than that is lost. Further, if we go out of focus, or if we have any aberrations, any non-ideal behavior in our lens, that too degrades the amount of information in the aerial image. Exposure, post-exposure bake, all of the resist processing from the point of exposure on, results in a latent image. Latent image like the aerial image, but it's the distribution of chemical species inside the photoresist. When we're done exposing, the aerial image is gone. The only thing that matters is the distribution of chemical species at the end of exposure. And so the latent image contains the information of the aerial image, but generally not a perfect representation. There's some information loss in that step. Development takes the latent image and turns it into a developed resist image, and then etching takes that developed resist image and transfers it into an etched image. At every single step in the process, there is information that is lost. So it's useful to define information metrics, metrics that define how much information is present in each of these steps. What we're going to do now is focus on the aerial image, and then we'll talk about other steps at the very end of this lecture. But first, the aerial image. What information is contained in the aerial image? Well, to do that, I'm going to relate the aerial image to Linewidth Control. As we saw last time, we can ignore higher order terms and assume small, uncoupled, independent errors in some process variable V, and we can say that the error, the uncertainty in the CD, the distribution of CDs, is equal to the error in the process variable multiplied by the sensitivity of CD to that variable. We know that not all processes are linear, but for many of them, in particular exposure dose we're going to talk about today, this is a good approximation. However, CDs are often specified as a fraction of the nominal. In other words, we say our goal is to print the nominal CD plus or minus 10%. So larger features have more wiggle room, smaller features have less wiggle room, less ability to withstand those variations. So instead of worrying about delta CD, what's really important in general in lithography is relative CD errors, delta CD divided by the CD. Well, if I simply divide both sides of the equation by CD here, I get delta CD over CD here, and I can turn my derivative into the derivative of the log of the CD. Well enough. But also we find that many process variables have errors that always occur as a fraction of the nominal. A very good example is exposure dose. If I have a variation in the illumination intensity over the photomask, that's going to result in a dose error. But that dose error is as a percentage of the nominal. If I double the dose, I double the amount of dose error I have as well, and I have the same fractional error change. So often we want to take our variable delta V and express it as a relative error. Now, not every process variable has errors that occur as a percentage of the nominal, but most do. So let's take delta V divided by V, and that means I have to multiply by V as well. That allows me to turn my V over dV into d log V. So for the case where we care about percent variation in CD, and for the case where errors in our process variable occur as a fraction of the nominal, then the bottom equation is in fact the total differential CD variability equation that's going to be interesting to us. And the process latitude term is going to be something like d log CD, d log variable, the term that's most interesting to us. So we will concentrate on exposure dose. And as a representative process variable error, and what we'll try to understand is what is d log CD, d log E. What controls it? What can we do to reduce it? This will be our metric of how much information reached the wafer about what the CD should be. Right? If d log CD, d log E is 0, that means even big changes in exposure dose won't affect the CD. I have infinite information. I know exactly what CD it should be, and nothing can change my mind. So, how are we going to get this d log CD, d log E factor? Well, we're going to start with the aerial image. And we're going to ask ourselves, what is a metric of aerial image quality? And I'll give you the answer, knowing that I'll be able to relate this metric of image quality to that exposure latitude term that we were looking for. So, I have a bright region, I have a dark region. And it's the goal, the task of the photoresist to place an edge, a resist edge, at the boundary between bright and dark. The key characteristic of the image that tells me where the photoresist edge should be is the transition from bright to dark. It's not how bright it is or how dark it is, but rather how much transition I get from bright to dark that determines where that edge should be. If I had an infinitely steep profile or aerial image at the edge, then I would know exactly where the edge was supposed to be. But because I have a profile that has a slope that's not infinite, I have some uncertainty as to exactly where the edge should be. So I'm going to use di dx, the slope, at the nominal line edge. Where I want the resist edge to be, what is the slope of the aerial image? But I have a normalization problem because if I simply doubled the intensity, I would get double the slope. That doesn't do me any good because I would end up having to cut my exposure time in half, and I haven't really changed anything. So I'm going to normalize out the effect of intensity by dividing by 1 over I, and that, if we remember our trig functions, di over I is the same as d log I, and this is called the image log slope. High values of image log slope means I have a good quality image. Low values of image log slope means I have a poor quality image. Then I will multiply this image log slope, d log I dx, by the nominal feature size. Let W be the nominal feature size. And I will now have what's called a normalized image log slope. Note that the NILS, the normalized image log slope, is a dimensionless quantity. That will prove useful. But the main reason that we multiply by the nominal feature size W is because we care about CD errors as a fraction of the nominal. And we'll see that and why that is true in just a minute, or why we need to multiply by W because that's true in just a minute. So this will be our metric, the NILS, the normalized image log slope, which is simply the image log slope multiplied by the nominal feature size. So, how does this image log slope relate to exposure latitude? Let me make it simple. Let me assume I have a perfect infinite contrast resist. Now, we talked about contrast a few lectures ago. Another way to think about an infinite contrast resist is a threshold resist. When the exposure dose reaches a certain value, all the photoresist washes away. But below that value, none of the photoresist washes away. I have a perfect threshold in dose that differentiates what portion of the resist will wash away and not. So if this is the exposure dose profile, exposing a wafer, and this is my dose threshold, all the doses above the threshold result in resist washing away, and the doses below the threshold result in resist remaining. And of course that tells me exactly what my CD is. Now, suppose I have a small error in the exposure dose. That's like scaling this whole image to a little bit higher, let's say, than it is now. Well, if it's a little bit taller, that same threshold will give me a slightly wider CD. So an error in exposure dose will produce an error in CD. All right, well, let's take a look. d log I dx, that's the log slope here. But d log I is exactly the same as d log E. Why? Because energy, dose, is simply intensity times time. And d log I times a constant, if I have a constant in there, d log E, the constant disappears and I get exactly d log I. All right, so the numerators here are exactly the same. How about dx versus dcd? Well, dx is how much one edge changes position. So I have a dose error, the edge moves. But if I have a symmetric image, same left and right, then that error will cause both edges to move in opposite directions, so that the change in CD is going to be twice the change in one edge. As a result, d log E dcd is simply 1/2 image log slope. Well, if I want to convert this to d log CD, I simply multiply both sides by the nominal critical dimension, and the result is, if I flip it upside down, d log CD, d log E is nothing more than 2/NILS. For the special case, of course the unrealistic case, the case that never really occurs, but for the special case of an infinite contrast resist. We don't have infinite contrast resists. We would like to, but we can't buy them. They cost an infinite amount of money. So we end up with finite contrast and non-perfect photoresist, and I'll talk about the impact of the contrast in a moment. But here we see in a very simple way how the NILS controls exposure latitude. Now, while we're looking at it, this term would be the slope of this curve if I plotted it on a log-log scale. Here I plotted on a linear scales, but if I plotted it on a log-log scale, this would simply be the slope at the nominal CD. Also, we can think of d log CD, d log E as the percent change in critical dimension for a 1% change in exposure dose. If I allow the exposure dose to vary by 1%, what percent change in CD will I get? Well, the best you could ever do is 2/NILS. So if your NILS was, say, 2 over 2 is 1, that means a 1% change in exposure dose would always result in a 1% change in CD. If the NILS get smaller, then I get a larger CD error for that same dose error. And if I make the NILS bigger, then my CD error goes down. That's why the image quality, the quality of the NILS is so important in determining the quality of the final result and the control we can get over the final result. Now that we know that the normalized image log slope is a metric of image quality that means something to us, we can use it. And one of the most useful uses of the image log slope is to look at the impact of focus on image quality. When we looked at focus a few lectures ago, we said that focus affects the aerial image in 3 ways. It makes the bright part of the image less bright, makes the dark part of the image less dark, and it makes the slope at the boundary between bright and dark less steep. Well, here we see that directly. The normalized image log slope, as we go out of focus, it is approximately quadratic, especially for small amounts of defocus. And then it stops being quadratic eventually. But we see that we can only tolerate a certain amount of focus. Eventually we have so much defocus that the image disappears completely. If the log slope is 0, it's flat. There's no information whatsoever about what the edge should be. So we need some higher level of image log slope, and this dictates how much focus we can tolerate. That is our depth of focus. Well, our previous discussion assumed an infinite contrast resist. What if we now allowed the resist to be real, have a finite contrast? Well, things get complicated, but a fairly good but still approximate model for how the image and the resist both affect our ability to control the CD is given by this equation. Note that gamma, the resist contrast, shows up here, and if I let gamma go to infinity, all of this goes away, and I simply have 2 over NILS, the infinite contrast result. If gamma is less than infinity, then my d log CD, d log E will be larger than 2 over NILS because I'm adding these terms to the 1. Note that there are 3 basic things going on, and one of them is the resist thickness D, or more particularly, the ratio of the thickness of the resist to the feature size, which we call the aspect ratio. So I have, in fact, 3 terms here. The first term is simply the aerial image dominated term, what I would get if I have an infinite contrast resist. You can't do any better than that. There's no more information available to us than the information that comes from the image. Then I have a term that degrades that from the fact that I have a finite contrast. So I get larger CD errors when the contrast is not infinite. But then I have a third term which has to do with this aspect ratio. And this has to do with the fact that getting good Linewidth control at the top of the resist is not what we need. We need good control all the way down to the bottom of the resist. So this last term describes the extra effect of having to develop down through the resist to get to the bottom, and then start worrying about how well can I control the CD at the bottom. Right? That's where this third term comes into play. Well, from this simple equation, we can see that there are 3 ways to improve exposure latitude, and there are therefore 3 ways to improve CD control. 1, I can make the NILS better. That is by and far away the best thing to do because it multiplies. You can see that not only does NILS show up out in front, but NILS shows up in all these other terms, so higher NILS always makes things better. I can increase gamma. Eventually I'll have diminishing returns as I go to higher and higher gammas, but nonetheless we can always benefit from an increase in gamma. Note that gamma is always multiplied by NILS. Gamma times NILS is the development rate gradient on a logarithmic scale, and that is controlling all of these factors that get thrown in there. And finally, we can decrease the aspect ratio of the feature, D over CD. If I use a thinner resist, then this last term gets smaller and smaller. Well, that is our lecture on lithographic quality and how a metric about image quality affects exposure latitude. Let's see what we've learned. As always, you should be able to quickly and easily answer these questions. If not, please go back and review the material. What are the 4 categories of lithographic quality that we discussed? Why is line width versus dose often characterized on a log-log scale? What's the advantage of a log-log scale versus a linear scale? What metric best characterizes the quality of an aerial image? And for an infinite contrast or a threshold resist, how is the CD sensitivity to dose related to NILS? Well, that's our topic on CD control and lithographic quality. Starting next time, we'll begin some lectures on a very interesting topic, resolution enhancement technologies. Till then.